Hello and welcome to this video summarising our paper, Who Left the Dogs Out? A new method for end-to-end 3D dog reconstruction. My name is Benjamin Biggs and I'm from the University of Cambridge in the UK. This first slide shows some results from our method. As you can see, we begin with a single monocular image of a dog and derive a full 3D mesh reconstruction in real time. The reconstruction of articulated subjects, such as human bodies, has been an important focus of computer vision research. However, there is still relatively little work devoted to reconstructing general animal categories. Human reconstruction pipelines typically make use of rich and plentiful data sources, such as 3D deformable template models built using real human scans, paired 3D data for each training example, and large 2D key point datasets which help models generalize to in-the-wild scenarios. Unfortunately, such large-scale datasets do not yet exist for animal categories. Animal-based techniques often make up for this lack of available 3D data by making use of artist-designed shape and pose priors to regularize their 3D predictions. While such priors have been shown effective for animal categories with more limited diversity, such as cows and zebra, they poorly represent more challenging categories, such as domestic dog breeds. Existing techniques for quadruped reconstruction typically incorporate slow energy minimization procedures, rely on hand-clicked key points for test images, or require video data for training, which can help constrain shape fitting. Perhaps again due to the scarcity of annotated data, evaluation of animal-based pipelines is often limited to non-standardized and small-scale test sets, typically of only a few dozen images. We first proposed dogs as an interesting category for 3D reconstruction, due to the large body shape diversity between breeds, frequency of challenging poses, and prevalence of nuisance factors, such as environmental conditions or interactions with humans and other animals. We solved the 3D reconstruction challenge by introducing an automatic and entirely end-to-end method for articulated animals, and demonstrate state-of-the-art performance over competitive energy minimization approaches, even when they are given access to ground truth test time annotations. Further, we introduced Symbold, a new 3D deformable dog model which includes limb scaling parameters and comes with a detailed shape prior, particularly suited for diverse dog breeds. We demonstrate a novel approach for refining such a shape prior by applying expectation maximization update steps during the training loop of our 3D reconstruction network. Finally, we released Stanford Extra, a new dataset of 2D key points and silhouette annotations for animals, and is currently the largest of its kind. We begin by discussing Symbold, our new 3D deformable dog model, which consists of shape parameters to represent the diverse dog body shapes and pose parameters that affect the limb positions. We extend Symbold from the original small model by making a number of adaptations to improve the model's representational power over the challenging dog category. Our first improvement is to add limb scaling parameters to improve the flexibility of the model by allowing variation beyond the original blend shapes. We introduced 6 new scale parameters which govern 2 directions of scaling over 3 body part groups. Furthermore, since the original small shape prior is constructed only from artist-built scans, we take steps to refine this prior using real 2D image data. We first adapt the existing small shape prior to use a Gaussian mixture distribution, which we then refine during our model's training loop using expectation maximization. As previously mentioned, our shape prior is constructed as a mixture of M Gaussians, where each Gaussian cluster has a mean, covariance matrix, and a mixture coefficient. We use this prior to regularize our network's 3D shape predictions by applying a loss to maximize the likelihood of predicted shape parameters under the mixture model. Unfortunately, as the mixture is initialized from a few artist-generated scans, the starting state lacks realism and is too restrictive for the diverse set of dogs that we wish to reconstruct. We therefore employ a procedure to improve the quality of this prior by learning from real image data during training. We begin by associating a vector of soft cluster assignments to each training image. Every k epochs we perform 2 steps. The expectation step recomputes the soft assignment weights for each image according to which clusters best explain the network's latest shape predictions. The maximization step then recomputes the parameters of the Gaussian mixture using the latest predicted dog shapes and soft assignments taken over the whole training set. The effect of this process is that the shape prior incrementally increases in realism during training, since the refinement steps are guided by learning from our large 2D image dataset. We will now introduce the architecture of our weakly supervised 3D reconstruction network. We begin with a single monocular image of a dog and use a ResNet encoder to generate a feature map, which is processed by linear prediction heads to generate the symboled shape and pose parameters and parameters for a perspective camera setup. During the training loop, we generate the symboled dog mesh from the set of predicted parameters and differentiably render key points and a binary segmentation mask to form losses against our ground truth annotations. Note that the network does not use any 3D supervision from real data. In order to encourage realism among our predicted dog meshes, we make use of pose and shape priors to help regularize learning. As mentioned in the previous section, we regularly apply expectation maximization steps while the model is training to allow our shape prior to adapt to the real 2D image data. We evaluate our method on a novel dataset, Stanford Extra, a new large-scale dog dataset complete with annotated 2D key points and segmentation masks. We chose to collect annotations for the existing Stanford dog dataset and an image repository containing 120 breeds of dog captured in the wild. The dataset contains many examples of challenging poses and difficult scenarios which stress reconstruction systems. We hope other researchers will make use of this dataset to form a standard evaluation benchmark for various 2D or 3D animal tasks. We use Stanford Extra as the primary basis for our evaluation. Note that our method performs well at reconstructing the 3D shape and pose of the dog, despite not having any paired 3D data for training. The figure shows that our method performs well at reconstructing the diverse body shapes present in our Stanford Extra test set, and copes well with difficult poses, various scenarios, and moderate occlusion. We also evaluate how well our method generalizes to an unseen data domain and test on dog images taken from the recent animal pose dataset, a much smaller dataset, but also contains 2D key point annotations. Note that we train only on Stanford Extra and do not fine-tune in any way. Despite the new domain, our method's performance does not considerably degrade, indicating our network builds a strong prior over general dog shapes. We next compare our approach to two optimization-based procedures, SMAL and CGAS. In order to fairly compare, we produce sets of predicted key points and silhouettes for SMAL and CGAS, rather than providing the competitors ground truth annotations at test time. We outperform both competitors, which tend to rely heavily on good initializations and struggle to cope with occluded body parts. This table reflects our improvements numerically, showing that our method produces improved silhouette coverage and reprojected key point accuracy than the competitors. Encouragingly, we also see our method outperforms competitors when we allow them access to test time ground truth annotations. Note that our method only takes a 2D image at test time. The final experiment we present in this video is an ablation study, in which we systematically remove various components from our method and evaluate the effect on the final metrics. We start by examining the effect of removing our EM update steps. Next, we replace our Gaussian mixture shape prior with a simpler unimodal version. And finally, we remove the scale parameters from symbols. We show that the average performance decreases with every component removed, except for one case. The second row in the table indicates using the Gaussian mixture prior, but not using EM refinement steps, produces slightly worse performance than using the simpler unimodal variant. We suspect that this is caused by a poor initialization of the mixture prior, which, without EM, remains fixed throughout training and produces suboptimal regularization of the 3D predictions. In summary, we have introduced an automatic end-to-end approach for 3D dog reconstruction and demonstrated state-of-the-art performance over competitive methods. We have shown our new symboled 3D deformable dog model and how to use EM to learn a detailed shape prior that represents a diverse category of 3D shapes. Finally, we have introduced Stanford Extra, a new large-scale 2D dog dataset, which we hope will be widely used by other researchers in the future. Many thanks, and we hope to see you at the upcoming Q&A session.